Hello guys, in this video I will address this important question. What really is an asymptote? What is an asymptote formally speaking? Because at this moment our understanding of asymptote is basically just at an intuitive level and we haven't formalized what this is mathematically speaking. So this question was raised by Aranza and some other classmates, and I started to answer this question in that group, but I didn't have time to finish. So here it goes. I'm going to explain to you the formal definition of an asymptote, particularly for horizontal ones and vertical ones, because there are other types of asymptotes. And then once I explain that to you, we're gonna check another four examples in case you want to check them. We have gone in most classrooms. I have gone through most of these, all right. But here they are in case you want to review them once again or look at them for the first time. For example, in classroom 603, I haven't seen this type with a square root. So let's start, guys. So let's read first. The concept of an asymptote is one that must involve a function. You have to understand that, guys. So what I'm trying to say is this. There are no lines that are asymptotes in and on themselves. If somebody draws um, a line in a Cartesian plane, so you have the Cartesian plane, and I don't know, let's draw this horizontal line. You cannot say that this is an asymptote because the very concept of asymptote should involve a function. It's a relationship between a function and a line that we will call the asymptote to that function. But if you just have a line like this and no other function to talk about, you cannot say that this line is the asymptote to anything. All right? You must have a function such as perhaps something like this, some function that behaves in this way, getting closer and closer and closer and closer to this line, and therefore we can call this an asymptote because this behavior is happening for this particular function, for this particular blue function. Maybe for another function which I can draw in red, this other function, parabolic function, this line is not an asymptote to this function. So you see, you must have a function and then a line to say whether that line is an asymptote to that function or not. But there is no line such that you can call asymptote just like that. That's impossible. Okay, that's the first thing. Let's continue reading. Now, that thing of an asymptote is a line which the graph of a function approaches but never touches, is a half-truth. Okay, that's how we started to understand, to get a feel for what an asymptote was. But it's not true. It's not true. It's just a half-truth, guys. In some cases, that's correct. This sentence is correct. But in the general case, it's not. Okay, and in mathematics, there are no half-truths. If something is a half-truth, in mathematics, we call that a lie. Okay, so this is basically a lie. So why did I tell you this? Why did I tell you that an asymptote is a line which the graph of the function approaches but never touches? Because for starters, the previous sentence is an okay understanding of an asymptote for starters, okay, to just to begin with. But in the general case, it's false. Okay, just like I write here. Nevertheless, it is a superficial and simplistic way to define it. And it is formally wrong. It is mathematically wrong because the graph of a function can actually touch one of its asymptotes. Okay, it actually can touch the asymptotes. Let me show you some examples. So here we have a function f whose graph is here in red, and we have its asymptote in blue. Take a look at this function. I'm going to zoom out a little bit. Zoom out, zooming in. I'm going to move the function around. And observe how the graph of the function gets closer and closer to the asymptote. Closer and closer and closer. And you can keep doing this for many minutes. And if you zoom in properly, you will observe that the function never touches the asymptote. So this may give you that idea, right? The one we started with, that an asymptote is a line that is not touched by the function. But that's incorrect. That is incorrect. In this case, that happens. But what about this? We have this function, once again in red. This function we say that has three branches. This is the first branch. This is its second branch. And it ends abruptly here. And then we jump to this other branch. All right? So three branches for this peculiar function. And this function has two asymptotes. This one in blue, which is y equals 2, and this one in green. I don't know if this is green, but I'm going to call it green. Y equals minus 2. And as we can see here, the function, which is this, this branch is part of the function, actually touches right there. It touches the asymptote. Okay, so in here, our previous definition breaks down. You see? So in fact, even though this is an asymptote to the function, as you can observe from this behavior in this branch, look at this. This branch does get closer and closer and closer and closer to that blue line, okay? But this other part of the function actually crosses the asymptote. Okay, so I'm sorry guys, there is noise outside CDEP, so I cannot help it. I don't know if you can hear that noise. I can. Okay, so I'm gonna continue. So yeah, a function can actually touch one of its asymptotes. Okay, so this is a more general case. That's my point. And even can present this type of behavior. Look at this function. This is a complicated function, right? Sine of x times e to the minus x over 50. And take a look at this function. We have the x-axis, the y-axis. I'm gonna zoom out and observe this type of behavior. This is an oscillatory behavior. The function is going up and down, up and down, up and down. Look at that, you see? But the oscillation gets less and less and less when you move towards infinity in the x-axis. When you move in this direction towards infinity, you can observe the following. The oscillations, in other words, the values of the function get lesser and lesser and lesser. Look. Can you see that? Can you see that behavior? So what's happening here? The values of the function, even though they are crossing, there is one crossing, there is another crossing with the blue line. Nevertheless, we can observe that the values of the function, all of these values, get progressively closer to this particular value in the blue line, which is 0, right? So you see? So basically, let me go here when I can draw better in here. So basically, as x approaches infinity, these values of the function, these distances, in other words, these distances get closer, on average, get closer and closer and closer to that particular value of 0. Can you see? Closer and closer and closer. Even though the graph of the function crosses the blue line many times. Can you see that? Okay, so we also say that this blue line is an asymptote to this function. Okay, so what is the formal definition then? What's happening here? What is happening is the following. Let's see. So then what really is an asymptote? I'm gonna give you the formal definitions of two types of asymptotes, the horizontal ones and the vertical ones. Those are the ones we will study. There are more types of asymptotes, but we won't study those. What other types? For example, this one. Look at this asymptote. We have this function. It has two branches, as you can see here. And you can see this blue line. Okay, and look, it's an asymptote. okay, because the graph of the function gets closer and closer to that value, all right? But we won't analyze this type. These are called oblique asymptotes. We won't study this type. Okay, so I'm not gonna give you the formal definition for these ones. Okay, so let's see. What is the formal definition of a horizontal asymptote? It's like this. First, suppose you have a function y equals f of x, and if that function satisfies the following two conditions, either, I should say either of the following two conditions, okay? Why do I mean by two conditions? I mean the case with the plus and the case with the minus in here separately. When you see this type of thing, guys, what I'm basically saying, or what mathematicians are telling you, is this, that you should consider the case with the plus. This is the same as this. The limit as x approaches infinity of f of x equals k, or the other case, the limit as x grows towards minus infinity of f of x equals k. Okay, these two statements, this one and this one, are compressed into this one, right? Just to save space, kind of like that. So we write the plus and the minus, and this tells you consider both possibilities, like so. So if a function y equals f of x satisfies either of the following two conditions, okay, that the limit as x approaches either plus infinity or minus infinity is a particular value, a particular real number, then we say that the line y equals k, and look at this, k is that particular number towards which the function approaches. Then this line y equals k is defined as a horizontal asymptote to the function. This is the formal definition of a horizontal asymptote. Okay, how can we say that y equals k is a horizontal asymptote to any function f? When this happens, when you evaluate the limit of that function as x grows either towards infinity or towards minus infinity, and if you get that value k in here, then we can safely say that y equals k is a horizontal asymptote. This is the formal definition. Okay, and on the other hand, the formal definition of a vertical asymptote, let's say it's quite similar. If a function y equals f of x satisfies any or either, okay, either of the following four conditions, the limit, look at this, the limit as x approaches either a or, I'm sorry, I made a mistake in here. This is incorrect. That's what I meant. I'm sorry, guys. Okay. So if the function satisfies any or either of the following four conditions, the limit as x approaches a from the right or from the left of the function is equal to either infinity or minus infinity, then we say that the line x equals a, this a, is a vertical asymptote of the function. Okay, and why do I say that there are four conditions contained in here? Well, you must consider all the cases. Plus and plus, that's one case. Plus and minus, and then minus and plus, and minus and minus. So in this very economical symbol, you are basically putting all of these cases. The limit as x approaches a from the right of the function is equal to infinity. That's the first one. And then the limit as x approaches a from the left of the function is equal to infinity, right? And then the other ones, the other two, when we approach a from the left of the function, is equal to minus infinity. and the limit as x approaches a from the from the right and then from the left of the function is equal to minus infinity. All of these four cases, guys. All of these four cases. Okay. All of these four cases are contained in this one single neat symbol. Right? And if any of these cases is satisfied, if any of these cases is satisfied, then we say that the line x equals a, you see, is a vertical asymptote of the function. What does that mean? It means that for this particular vertical line, guys, for this particular value of the function of the variable, which is a, for that particular value, the function blows to either infinity or minus infinity. It shoots upwards like crazy, or it shoots downwards like crazy when dx gets closer and closer to this particular value a, either from the right or from the left. This is, let me clean this up. This is the formal definition of a vertical asymptote. Okay? So that's, now you can understand now you can understand why I cannot give you the formal definitions until we consider the idea of limit with more precision, right? If you don't have the idea of limit in your mind, then you cannot understand the formal definition of these asymptotes. You see what I mean? That's why back then I couldn't give you a proper definition for an asymptote, and I lied to you, because in order to make that definition, I need to lay down some other territory, the territory of limits. That's the reason, and this happens in mathematics a lot of times. You first have some superficial understanding of an idea, and then you work harder in order to formalize the idea. And after you make the formalization, then you make your definition of the previous concept that at first you only understood in a very vague and intuitive way. This is how it happens, guys. This is how it happens. Okay, intuition, a lot of work, formalization in mathematics, and then we define the concept that we started with in a much cleaner and precise way. This is how mathematics works, and sciences too. All right, perfect. So now let me address these examples, these four examples, maybe in a part two, because I'm gonna go to class right now and I need to cut this video. So in a part two of this video, I'm gonna call this part one, the next one part two, and I'm gonna give you I'm gonna go over these four examples again. Okay, these types of rational functions and how to find their horizontal and vertical asymptotes using the definitions, the formal definition of a horizontal asymptote and the formal definition of a vertical asymptote. Okay, so that's what we'll do. Thank you, guys.